We had a quadratic, and we had one that looked like this. Oh, I want to get it. And then we had one that looked like this. And then we had one that looked like this. Do you remember this, everybody? The zero stayed the same, but we flipped it over and made it steeper. What did we put out front of this thing? What did we multiply by? Any constant, any n value, right? The bigger you make it, the steeper it gets. Does it change the zeros? No. 0 times anything is what? As long as it's multiplied, right? So as long as I'm multiplying by some constant c, it doesn't change anything other than every other point. So that's how you would do the bonus question. You would plug in, I think it was like 80 here. And you'd have a times, and I think it was like 6. You plug in 6 for all of these x values, and then you find out what the coefficient is. And I set it up so that the coefficient was a nice number. Should have been a nice number. But yes, I would either have accepted this or multiply it out. Absolutely. I didn't force you to do either. I didn't say specifically, so I would accept either one. Yes, Tyler?
Do you have...
So assuming you can place the tether anywhere along the side of the barn, where should you place it? And this is the really good question, the really important part. And why? Maybe it is this. Maybe this does maximize it, but prove it. You definitely can use your calculator. Okay, to use calculator. Here's a way.
What if the best way is a decimal?
Well, then you're gonna have to use. That's what your calculator is gonna help you with. You're gonna make an equation and then use your calculator to find a max or min. Okay. Also, then you can also. I mean, similarly, what's the minimum value? Like, how do you want the cow not to like you? I don't know. One of my upper level calculus classes. This cow problem is a really classic geometry question. What happens if you had like a rectangular prism floating in space? And you had a cow tethered to the corner. Let's say this was like 20 by 20 by 40. And you had a 50-foot lead, and you had your cow with a spacesuit on like this, like, moo, right? The question is, like, what volume does he have access to? What volume does he have access to? And you know that the volume of a sphere is what? 4/3 pi r cubed. Do you remember that ever? Yeah, it's 4/3 pi r cubed. The point is, you get a lot of, instead of a lot of quarter circles, you get a lot of quarter spheres. And we tried working on this in multivariable calculus, like what's the best place to put the cow on the edge of the barn, like anywhere on the surface, like you could anchor it here or there. It gets really complicated. It gets really complicated. What's really cool is to imagine like what shapes you make. Like this shape right here. This shape right here is one of the shapes you get in 2-dimensional, right? So what happens when you do it in 3 dimensions? You get like a bubbly surface. It's kind of cool. It's kind of cool. Is equal to the hypotenuse squared. So you have 4r squared plus 4r squared is equal to h squared. So h squared is equal to 8r squared. So h is equal to the square root of 8 times r, correct? Well, we know that what's this length right here? R. And what's this length right here? R. 2r plus 4. So we know that h is equal to 2r plus 4. So we have h is equal to root 8 r, and h is equal to that, so we can set them equal to each other. So how do we solve for r? Yeah?
Subtract 2r from both sides.
Sure, so you get 4 equals r root 8 minus 2r. Yep, now what? Do not divide by anything. What do I do now?
Yeah, factor out r.
Factor out r. Yay. R times root 8 minus 2. Divide both sides by. So you get r is equal to 4 over root 8.
Minus 2.
Really?
How'd you factor out r? I'm not sure.
Hold on. How'd we do what?
Before you factor out r, I don't get...
Okay, do you understand how we got this? Right here. I'm sorry, you can't see what I'm doing because it's not circling. Do you understand this? Yeah. This? Yeah. We have h is equal to 2 different things, so we set them equal to each other. Yeah. So are we good here? Yeah. So then we subtracted 2r from both sides, so minus 2r, minus 2r. Factored out the r, so r is equal to 4 over that. Hold on a sec, you might not be wrong. So this is r is equal to 4 over 2 root 2 minus 2, right? So that's 2 times 2 over 2 times root 2 minus 1. What cancels? one of the 2's, right? So r is equal to 2 over root 2 minus 1. But here's the thing, everybody. Here's the thing. Do we like having square roots in denominators? We generally don't. We like to get rid of them. What's the only thing we can multiply by? What's the only number we can multiply something by and keep it the same value? 1. So we have to multiply by a form of 1. Anybody want to take a guess as what we multiply this by? Yeah. Good guess. Almost. Yeah? Yeah, root 2 plus 1 over. If you do that, what does the top become? 2 root 2 plus over. What's root 2 times root 2? 2 minus root 2 plus root 2 minus 1. What cancels?
The root 2's.
Okay, hold on. I don't want to do this too fast. I'm sorry. Ready? 2 times root 2 is 2 root 2. 2 times 1 is over. What's root 2 times root 2?
2.
Root 2 times 1. Negative 1 times root 2. Negative 1 times 1. Minus 1. Yeah, minus 1. So what do you actually end up with? 2 root 2 plus 2 all over what? 1, which is just 2 root 2 plus 2. How many people got that? You got that? One big kid way to write it would be 2 times root 2 plus 1. That's another way to write it. And did you get that? Awesome. Cool. So you understand how we set that up? Kinda, maybe, sorta? Kinda, maybe? Okay. Good.